What you're seeing here is a vision of the future, a combination of technologies being developed into one comprehensive package that allows for one person to design a house, store it for later recall, run the design through a simulation graphics program, test the feasibility of actually building such a design, and then build it, all from a single computer workstation without touching a log or writing a single line of computer code. Just one project of the Center for Productivity Enhancement, this is the University of Lowell's Factory of the Future. The Lincoln Log Factory of the Future is just one example of the center's holistic philosophy, studying the manufacturing process from the initial design and engineering of a product to its manufacture, striving to involve both industry and academia in mutually beneficial projects and partnerships. Established as a means of combining engineering education with an exploration of technological advances and a determination of how best to apply these technologies, the goals of the Factory of the Future are several. To understand the laws and principles of intelligent production, to know the limits and variables of these principles, to determine the potential of artificial intelligence and expert systems, to establish specifications that allow for rapid expansion into the private sector, and to develop a software library of intelligent manufacturing tools. This project has been cited as being more advanced than any factory reported in current literature. As a research tool, it has shown that while its product is a toy, and its expert systems are based in part on watching children play, it is a robust, intuitive model of what computer-integrated manufacturing can be. The factory itself is made up of three parts: an intelligent computer-aided design or CAD system, a simulator, and the physical factory. Consisting of a color monitor, a keyboard, and a mouse, the CAD software displays a grid and icons of logs, which the user selects and places on the grid with the mouse. Structural requirements and integrity are checked automatically by the software, dictating allowable choices for the next log placement, thereby avoiding expensive mistakes. When a house design is completed, the CAD system creates a list of the parts used and their positions, all in English. This file becomes the source for the simulator and for the physical factory. The simulator is a computerized graphic representation of the physical factory, complete with logs, robot arms, and a workspace on which the Lincoln log houses are built, even gravity. All laws of structural feasibility apply, as the simulator runs through a make-believe construction of a house. Physically, the factory consists of two cooperating robot arms with a work pallet between them, parts feeders at each robot's side, and video cameras. This is a machine vision-aided system, utilizing two video cameras mounted from above to oversee the work pallet, making sure that the logs have been placed correctly before allowing construction to continue. The actual construction is controlled by an expert dynamic scheduler program, which directs the robots and parts feeders as they work to build a house. The parts feeders use pneumatics to advance one of the three sized logs to a place where the robot can pick it up. The scheduler determines which arm lays down which log at any given time, actually making decisions about how to build the house. In fact, it might not build the same house the same way on two separate executions. It makes its decisions on the fly. The system has a built-in error simulation process controller called Gremlin, randomly causing problems which the scheduler must then solve in real time. Here, for example, Gremlin has shut off one of the log feeders. The scheduler makes its plans accordingly and directs one robot to pass the other robot a necessary log. Here again, we physically intervene and move a log after it has been placed. Noticing that something is amiss, the scheduler then redirects the robot arm back and it repositions the log. Note that the elements of the factory are simple, with low-tech components, and that the system software has to compensate for their inadequacies by performing error corrections. Students design the various strategies, such as this wiggle routine. This is the control center of the operations, a video information processor, from where a single controller can oversee numerous factory workstations. Each work cell is equipped with two side cameras, allowing the